For those who are already familiar with LTADchat on Twitter and our live Zoomcast, this is our short tutorial format where we use the concept of a picture is worth 1,000 words, allowing guests to show concepts in a slideshow. Today, I'm excited to have my good friend and colleague, Professor Adam Baxter-Jones here to share his expertise on growth and maturation, and specifically the adolescent growth spurt, and one of the ways called the maturity offset to assess age at peak height velocity or estimate it in a feasible manner. Before Adam dives into the maturity offset equation for estimating time away from peak height velocity, I'm going to have him start with a discussion about his history, specifically related to studying with Professor Jim Tanner, conducting the study called Training of Young Athletes, or TOYA, and then rolling right into this idea of the maturity offset. And then after that, we'll let him keep going and discuss the methodology to derive the maturity offset, or the Muir-Wald equation as it's become to known, and give an example from their website. Adam, welcome.
Thank you. I'm delighted to be here and looking forward to showing and sharing a few pictures with everyone. So just to give a history of my story, so I worked on something called the Training of Young Athletes study in the UK in the late 80s and early 90s. Now, this was a study set up by James Tanner, who I'm sure we're all aware of, most notably for his work with secondary sexual characteristics, which ended up with the label of Tanner staging. But at the same time, and in this picture you can see in front of you, I also worked with Michael Priest, who took over from James Tanner during my period. This is all at the Institute of Child Health in London. And Mike Priest, you should be aware, is well known for the development of the Priest-Baines model, which is a mathematical model of the adolescent growth spurt. Now, really, when I was doing my work, and this was doing my PhD in the late 80s, 1990s, most people who were trying to control for maturation used James Tanner's measures of secondary sexual characteristics. And again, this is illustrated here, where you would either visually take an assessment of a 5-stage of secondary sexual characteristics, was displayed in this slide here is pubic hair growth in females, and these are in 5 stages. Now, of course, it's very invasive doing this type of technique, and you really require some sort of medical backup to the work that you're doing. The other disadvantage of this technique is, well, it was developed really in clinical settings, and the 5 stages are not continuous. You don't really know where someone is in terms of their staging when they walk through a door. You might visually assess it and then it changes the next day, or it might change 4 or 5 months down the line. And again, the invasive nature is problematic. But working with Jim Tanner and Mike Priest, we did use these measures. We had a medical group, and this is shown. You can look this up in the Training of Young Athletes study. There's a review paper in Pediatric Exercise, which came out in 1996. And I just wanted to highlight to you a couple of the descriptive statistics. And this was in a paper in the Annals of Human Biology in 1995. On the top right-hand corner, you can see a graph of testicular volume. So the testes are the first overt sign of sexual development. And these are on normal reference centile charts. So the middle dotted line is the 50th centile. And we have 4 groups here of different sports. And what this graph is really showing is that the majority of individuals followed a normal curve, to swimmers and soccer players. But early development, so when you push your line to the left-hand side, is shown by swimmers, and late development is shown by gymnastics. And then if you look down below, you can see development of genitalia stage for gymnasts, and swimmers are 2 extremes. And again, it shows you similar to testicular volume. And this is the important thing to remember, is that all sexual milestones are very similar, and so similar patterns. So advanced in swimmers, slightly later in gymnasts. This graph here is just illustrating, this is taken from Tanner's work, Fetus into Man, for males and females, is when all of these things occur. So in terms of pubic hair and genitalia rating, I'm showing you here, on the left-hand side is the female. You can see that breast development starts at 8 to 13 years of age and is completed by 12 to 18. And in boys, testicular development starts somewhere between 9.5 and 13.5 years, finishes about 13.5 to 17 years. So there's great variation. I put this slide up just to illustrate where peak height velocity is occurring. So on the top part of this graph, you can see that there is a growth spurt during adolescence, which most of us know about, and it occurs in girls somewhere between 9.5 and 14.5 years, and in boys 10.5 to 15 years. Now, when we're looking at development, what's important to remember is that when you're looking at peak height development, you are actually looking for a change over time. And so for that, to get the tempo of growth, you need longitudinal data. And myself and Joey and a colleague from the University of Loughborough, Lauren Shearer, produced a paper, and this is 2005, where we actually reviewed all the different measures which control for maturation. And so we're not talking about that today, and I'll send the readers, the listeners, I should say, to have a look at that paper to give an overview of all the various methods. Having worked in growth and development in Jim Tanner's lab, I then had the great opportunity to move to the University of Saskatchewan. And the University of Saskatchewan is well known for two major longitudinal growth studies. The Saskatchewan Growth and Development Study that was conceived in 1963 and then initiated in 1964 and ran until 1973. And since then, there have been various follow-up measures. And these basically followed a group of boys and girls between the ages of 8 and 15 years of age. And so we were able to follow their growth, in particular their peak growth during adolescence. That was the first study that was initiated in the college and the picture here is Don Bailey, who initiated this study. And then he conceived and created a second longitudinal study called the bone mineral accrual study. And he initiated this with his colleague, Dr. Bob Faulkner. And these had longitudinal measurements. But the difference between the two studies was the first study was looking at physical performance in young children and its development. The second study was looking at bone development. And as you can see from the dates below, these studies we've gone back to these individuals on numerous occasions. So ultimately what we're looking at, and is what people see, is that you'll have a group of boys or girls of a similar chronological age, and that's illustrated in this graph here. So we have boy A through to boy I. These all have a chronological age of 14 years. In fact, the age difference between boy A and boy I is roughly about 4 months. However, the difference in stature is closer to 35 centimeters. So you can see there's vast differences between individuals of exactly the same age. The boy E, the one right in the middle, represents the 50th centile and is the average height for that individual at that age. One of the things you can do is if you do actually know, the other thing you should be aware of is that as a percentage of growth, by 18 years of age, boys are fully grown. Sorry, I should say it again. By 18 years of age, girls are fully grown, and by 20 years of age, 21 years of age, boys are fully grown. This table here is just illustrating the percentage of growth that occurs as you get older. The pink line is the 12 years of age. This is where girls reach their peak height velocity. And you can see that they're roughly 93% of their adult height, whereas boys who reach their peak 2 years later are roughly about 92% of their adult height. So it is possible, therefore, when you look at boys we just showed you previously, to see how far are they in their maturational growth. So here we have the same data set that I just showed you. These are 7-year-old boys. Here they are, exactly the same boys at 14 years of age. So what you can see is at 7 years of age, boy B is the shortest and boys A and C are the tallest. You go up 4 years to 14 years of age, so roughly when peak height velocity is occurring, and you can still see that difference between A, B, and C, where B is the shortest boy and A and C are the similar size. And so what you could conclude from this is that boys A and C are more advanced in their maturation. This is purely based on morphological size. However, if we look at these boys at 40 years of age, so remember we keep bringing these individuals back, it's now quite obvious from that 40 years of age that boy C is considerably taller than boys A and B, and that in fact boys A and B end up being the same height. So this is the important thing about growth, is looking at the timing and tempo. Knowing where people start and where people end is what we're really looking for. Taking that pictures and actually making it graphically, what I'm showing you here is their actual heights at 7, 14 and 40 years of age, but this time aligning it to their adult stature. So again, you can see that boy C at 40 years of age is considerably taller. What's important is that at 14 years of age, boys A and C at 97% of their adult stature and 89% of their adult stature are actually closer to maturation. And this is important because before we were saying that the middle boy was closer. So this is really to illustrate that stature itself is not a good measure unless you know where someone's going to and where they've come from. So this leads us back to what we really wanted to talk about today, which is the adolescent growth spurt. This is illustrated, I've taken this illustration from Growth of Adolescence. Again, you can see that there's deceleration in growth. So this is velocity of growth, centimeters per year. There's a deceleration from birth. You then roughly grow about 6 centimeters a year during childhood, early childhood, 3 to 8 years of age. Then girls start growing at about 9 years of age. Exactly the same time, we're seeing their breast stage development, then we're seeing a steady increase in stature, and they peak at 12 years of age, and boys peak at 14 years of age. So this is really very useful as a measure of maturation. So I've told you before that we, at the same time as breast development, genitalia development, etc., which we used in the 1990s, but it became increasingly obvious that really you couldn't use this data in a field situation or coaches, physical education classes, etc. So really we needed a way to perhaps identify when peak height velocity was likely to occur. As I said, you need longitudinal data to do this. So this is some data taken from our own studies. First of all, you plot the velocity change. You then fit a mathematical curve to that change. And then using that mathematical data, you identify where the greatest velocity is occurring. And in this case here, you can see this individual is having the greatest velocity at 14.5 years of age. Now, as part of an undergraduate class that myself, and this is Bob Mirald, who was running the class, we plotted graphs continually of proportionality of growth. And a question came up in the class, so what is the relationship and the proportionality of leg length velocities to height velocities to trunk velocities? And this set us thinking about how could we use this information to predict when peak height velocity is going to occur. So again, this slide is illustrating the changes in body proportion. We can see that at birth, your head is half its adult size, your arms are 1/4 of their adult size, your legs are 1/5 of their adult size, and your trunk is 1/3 of its size. The other important thing to realize is that growth occurs from distal to proximal. So your feet and hands grow first, and then your arms and your legs are growing. And these are growing in advance of your trunk development. And so what this is showing is that there are differences in the proportionality of when you reach your various maximums and peaks. So taking that proportionality, and this time taking that same individual, so the top graph here shows that we have plotted their graph and showed they had a peak height velocity at 14.5 years of age. If we then plotted first of all, their leg length, we found that it peaked at 14.2 years of age. And if we plotted the peak of their sitting height, so that's your trunk length, so basically you're measuring height, measuring sitting height, and then taking the sitting height away from your height, you'll get a measure of leg length. So sitting height is a measure of trunk length. So you can see that the trunk length is occurring at 15.38 years. So here we have a relationship between the occurrence of these various peaks. First of all, your legs grow and peak, and then your trunk grows and peaks. And in between those two time periods, your height peaks. And this is the information that we took and said, okay, there's a pattern here. Can we use this pattern to give us some idea of when peak height velocity is occurring? So as I said, the issue is that you can see you need 4 measures or 3 or 4 measures to have a true height peak. And those 3 measures have to also go through the timing of when it's occurring. So in a field study or a cross-sectional study, you're never going to know whereabouts on the curve they are. Are they going up, increasing their velocity, or are they going down, decreasing their velocity? So that's what we looked at. And as I said, this was all done in an undergraduate class, having lots of discussions. And so we looked at the ratio, and this graph is showing here, of leg length to sitting height. And if you can see that this leg length to sitting height ratio peaked at 14.9 years of age, so fairly close to the peak of peak height velocity. So again, this ratio goes up before peak height velocity and then goes down after peak height velocity. So it did seem possible that using this leg to sitting height ratio on a one-off occasion, you could predict when peak height velocity was going to occur. So that's illustrated here. We have our leg length to sitting height velocity in our dashed lines, and I've just plotted it against what I showed you previously, peak height velocity. And those peaks are roughly occurring at the same time. So that's interesting, but does it really help? And the problem is that although this leg length to height, leg length to trunk length velocity gives you an indication of, the ratio gives you an indication of where you are, again, it doesn't tell you whether you're going up in velocity or whether you're going down in velocity. So it's not much better than a best guess. You actually still need 2 measurement occasions to allow you to tell you whether an individual has reached their peak, is pre their peak, or is post their peak. So not good for a single occasion prediction. So the next stage that we went into was Bob, myself, Don Bailey, and Gaston Bernon, professor from University of Leuven in Belgium. We came together and actually created a regression equation that was used to predict the age from peak height velocity. So using that knowledge about proportionality of growth, we tried to see whether we could predict when peak height velocity was going to occur. And I looked this up yesterday on Web of Science. This paper has now been cited nearly 1,000 times. So it's obviously being used by various people out there. So here's an example of the equation then. You need to know the chronological age of the individual, the height of the individual, their weight, the leg length, and sitting height or trunk length. And this is an example shown here. The other thing we looked at in this example, in this equation, was we also looked at various interactions. And we found that the significant interactions were leg length and sitting height, chronological age and leg length, chronological age and sitting height, and a weight by height ratio. And this weight by height ratio is basically weight divided by height times 100 to give you a percentage. So if we take that information for this individual at 11.2 years, put it into the equation is shown in front of you, you actually get a value. And this value says -2 is the value that's created from those coefficients and from those numbers. And what it means is that you're 2 years from when peak height velocity is going to occur. And this measure has been called the maturity offset. It is not, and some people have miscellaneously used it or labeled it, it is not, we do not predict peak height velocity. If you want to predict the age at when peak height velocity is going to occur, then what you would do is you would look at that so you're 2 years away from peak height velocity, then 11.2 years, that basically means that their peak height velocity is going to occur at 13.2 years of age. So again, just to emphasize, we're seeing how far you are from peak height velocity occurring and from when it's attained. And the error of this measurement is plus or minus half a year. We recommended in this paper that this measure was only accurate, really accurate, between -4 years from peak height velocity and +4 years. So in this individual, it would be from 15 years to, here's my maths, 8 years of age. No, 7 years of age. So you've got a sort of 5-year window of when you can actually say that this will work. The other important point is that the closer you are to the attainment of peak height velocity, the more accurate the equation is going to be. And for those reasons, because there is a lot of error, the paper does suggest that it could be used as a categorical variable. That is, if it's a minus number, then they're pre-peak height velocity. If it's a positive number, then they're post-peak height velocity. So it's a way of actually measuring a child's anthropometrics, height and weight and age, and saying how far they are from attaining, or how far they are from having obtained peak height velocity. And I'm just illustrating that here. This is the paper, Assessment of Maturity from Anthropometric Measures. And here is a diagram that's predicted, a Bland-Altman plot they're called, but has predicted the difference in the predicted value from the actual value. And what I didn't highlight was, of course, to actually produce these equations, you need longitudinal data to produce them so that you have an actual measure and then a predicted measure. And what this is really just saying is the closer you are to when the difference is occurring, the better, the more accurate the variability, really, the variability of the measure. Now, this is also being discussed by other authors, and Bob Molina did some work with some Polish boys. And I've taken the table here, so he did exactly the same. He looked at our equation. This is a longitudinal sample. What he found was that at 14 years of age, that the maturity offset gave a value of -3.2. So basically saying it's close. And the predicted value was 12.8. So a difference of 0.25 years. So that's well within the error of half a year that was suggested. The other important point in this paper is the fact that if you look from 8 to 18 years of age, the range in the mean differences decreases. So at 8 years of age, the error is nearly 1.5 years. At 18 years of age, the error is 0.8 years. But when peak height velocity is occurring at around 14, the difference is between 0.2. And in fact, at 12 years of age, you have a difference of 0.0. So what this is, as I said, so ultimately what has been concluded then, and this is another recent review article by Bob Molina and colleagues, and reviewing different ways of putting youth athletes banded by their biological age, how close they are to achieving full adult stature. And they concluded that the age at peak height velocity were later in the, this is using the maturity offset equation, later in the observed compared to the early maturing individuals, and earlier in late maturing individuals. So the actual maturity timing may have an effect on the offset equation, and that the equation had utility within a narrow chronological age range in average maturing boys close to the timing of observed age peak velocity. And so really what a lot of these papers, Bob Moline's papers, have shown is that the error is high the further you are from the event, which is what the original paper said. But really what they're saying is they really recommend it should be used between -2 years from peak height velocity and +2 years from peak height velocity. And then I just wanted to finish off then by showing you an example, a worked example. So at the same time that we produced the paper, we also produced a web page, as shown here. So on this web page, what we can do is we can predict the age at peak height velocity. So if we take an individual, let's say they're a male, we put in their date of birth, and I've got an example here of someone who was born in June 2015. So this is someone who came into one of our studies. They were tested in October 2017, and those two values will give you a chronological age. Their height was 152 centimeters. Their sitting height or trunk length was 81.2 centimeters, and their weight was 44.9 kilograms. So by pressing a button, just using that equation I showed you before, it gives you an output that tells you that the predicted years from age at peak height velocity, or the MAT off, is -1.2 at this measurement occasion. So their chronological age is 12.3, and what it's saying is that their predicted age at peak height velocity will be 13.5. So their pre-peak height velocity. And just to give you one other example, works exactly the same. If we look at a female, again, born in the early 2000s, tested in 2017, this girl had a height of 157 centimeters. So obviously taller than the boy that I just talked about. Had a sitting height of 83.9 centimeters and a weight of 42 kilograms. And this time, if we calculate their peak height velocity, first of all, we see that their predicted age is now 0.07, so it's a plus value, so peak height velocity has already occurred. They're 12.8 years of age. It occurred roughly 7 months previously, 0.7, and so this individual is post peak height velocity. So hopefully, Joey, that gives you a very brief outline as to how we've used measures of anthropometrics to predict a measure of sexual milestone that is occurring in both males and females. And it is a fairly unintrusive way of measuring what can be a fairly intrusive measure of sexual development.
Yeah, Adam, thanks for a great presentation of growth and maturation in general. especially from a historical perspective with your work with Tanner and then the Toya study in the 90s, and then into your work with the longitudinal studies at the University of Saskatchewan in the 2000s, which obviously included the development and the use of this tool called the maturity offset, or what some people also refer to as the Meerwald equation. Listeners can find more information on the maturity offset at the website just shown. Again, that's usask.ca/kin-growth utility. And you're always a Google search away from finding more of Dr. Baxter-Jones's work in growth and maturation. He's done considerable work on bone development. And Adam, I think maybe in a future episode, we'll have you back on and talk about bone development and exercise training. And also, I think we're going to have a little bit of a roundtable discussion or a fireside chat between yourself and our colleague, Dr. Sean Cummings, all things growth and maturation, because there's a lot of individuals, especially in the youth sports and long-term athletic development space, who are really getting an appetite for gaining a better understanding of growth and maturation. So that's something that our listeners can look forward to in the near future. So thanks again, Adam, for your time today, and we hope everybody enjoyed this episode of the LTAD Chat.
Thank you. I very much appreciate having this opportunity. Always a pleasure to work with you, Joe.